Just, I think the screen is too small. Can you see it well? Okay. Anyway, so let's start. Good afternoon, everybody. So last time, guys, I told you, let me bring this one up here. Yeah. As shown here, last time, last time I told you guys, any computer system should have memory. Is that okay? So, so this is the system. Microprocessor alone cannot make a system. Okay, so I have to connect the microprocessor, as you see here, to memory input-output devices to create a system. Okay, and as I told you last time, when I say computer system, I mean many things. Okay, many things can be considered like computer system. Okay, like the microcontroller chip, as you will understand in this course, it's a computer system. It has this architecture. Also, I told you last time, the reason we have memory here, as you will understand this better as I teach more in this course. The reason we have memory, because the memory should store two things. Number one, program. So your program has to convert it to machine code. So actually, your program is just a bunch of ones and zeros. And these ones and zeros are stored in memory. Is that okay? And what happens is that microprocessor, microprocessor should execute instructions. As I'm going to explain shortly, the processor is designed to execute instructions. So where are these instructions? They are in memory. So what happens is that microprocessor is going to ask the memory, give me an instruction, just a bunch of ones and zeros. These ones and zeros, okay, are going to be executed by the hardware, okay? Then once I finish this instruction, I'm going to go to the memory again. Please, memory, give me next instruction, and so on. And that's what we are going to see in the first lab. In the first lab, for sure, I didn't teach assembly yet, so I don't expect you to understand assembly, but I'm going to give you a program. Okay, just you are going to write this program, and you are going to see the machine code, the ones and zeros, and you are going to see them in memory, stored in memory. Is that okay? Also, memory should store data. So what do you mean by data? Any program should have variable, like similar to what you did before in C language, integer I, integer J. Also, any program can have arrays. You may need arrays. So where are all of these stored? Also in memory. Is that okay? That's why we need memory here. The processor itself, it does not. The processor itself, it doesn't have a big storage to store the program. That's why I store here outside here. Okay. One also, as I explained last time, the way it works is, okay. Yeah, that's what I'm explaining. This is the memory has instruction, and it has the processor has to read one by one. Also, I just want to show you here how it is connected. So there is data bus. This is like a chip. Okay, it's like a chip. This chip should have wire to connect the data bus this way. Also, we have here what we call address bus, should be connected to the memory this way, and also we have control. We have control bus. Okay, so how everything can work together. Okay, again, don't be confused. The data bus should carry data. Address bus should carry addresses. Okay, and here the control should tell the memory if you want to read or write, right? Because you can read or can write, right? So you have to tell memory can. It's not going to guess if you want to read or write. So you have to tell the memory, I want to read or I want to write. Okay, how can I do that? There is a wire, a connection this way. Okay. Also, I told you last time, you can imagine memory is like locations. As you see here, we have locations. Okay, every location is storing 1 byte. Okay, 1 byte. And when you read a byte or write a byte. Okay, so every location, and also every location has what number. So this location number 0, location number 1, location number 2. Okay, so every location has location number. That's what we call address. So I'm not gonna use the word, I'm not gonna use the phrase location number anymore. I'm gonna use address. So address here, the number. This number 1, number 2, number 3, number 4, and so on. Okay. And in every location we store one byte. Okay, and as I told you before, guys, when I say FF, actually physically it is stored 11110111. You understand what I'm saying? But just because it's easier for us, I'm writing it in hexadecimal because just easier. Yeah, let's agree on this. Okay. One more thing I told you guys last time, in our microcontroller, these addresses are 16 bits. Don't be confused. So we have two numbers now. We have two numbers. The first number is the address. This one is 16-bit. Is that okay? Second number is the data stored here. This is a byte. Okay. So yeah. So that means because addresses are 16 bits, that means how big is the space? How big is the space? As I explained to you before, if you have 16 bits, so you can have up to 2 to 16 addresses. This is all the addresses, locations we can have, okay? Because 16 bits can have up to 2 to 16 numbers, 2 to the power 16 numbers. So, and the whole space should start from 0000 dollar sign. So this dollar sign means this is hexadecimal, okay? And every, this is 16-bit, right? This is 16-bit because every digit here 4 bits, okay? So we start from address number 000 until address number FFFF. This is the whole range. Is that okay? Okay. One more thing here, guys. Actually, as you will understand later when I teach more in this course, actually, not the whole space. I'm going to use it for memory location. Some addresses here are going to be used for input-output devices. Okay. Think about it. The idea very simple. If you want to read or write, and you want to put address here, if you look at the system here. So if you put here an address, if you write an address on the address bus, this address can be an address for one input-output device, or it can be addressed here in the memory. Okay. So every one of them, so every location in the memory should have a unique identifier address. Also, every input-output device should have a unique address as well, because otherwise it's going to be confused. Okay, it's like if you have two people that have the same social security number. Okay, so it cannot work this way. So it should be that's why that's exactly what address is doing. Okay, identifier. Okay. One more thing I explained last time, guys, that here I told you every location store a byte. Okay, it may happen that your data or your information is 1 bit or 2 bits. Okay, for example, my information is 1 bit. This bit is coming from a fire sensor, or it's coming from alarm to tell me if there is alarm or not. It's coming from somewhere. Okay, so just 1 bit. So how I can store it? I cannot store 1 bit and I cannot read 1 bit. Very simple. You can read a byte or store a byte. Okay, because this is unit. It's a unit. Okay, so very simple. All what I'm going to do, guys, I'm going to bring a byte. I'm going to use this bit as you see here. This is a byte. Just I'm going to store my information here. Okay, and then write it. And when I read, I'm going to read the whole byte, but I'm going to only look at this one because I only care about this one. You understand what I'm saying? So you can do, because you have to write a byte or read a byte. Okay. Also, I told you last time, guys. Now, what if your data is more than a byte? It may happen that, or it's going to happen in many cases. Okay, because this is, you have to decide, because in your program it's similar to what you did before in C language. You have integer I, or you have long or short. Okay, how can you select integer or long or short? How can you do that? Based on your variable, how big the data will be in this variable. Okay, you should have learned it in C language. Integer should have a range. If your number is bigger than that, you have to make it double, right? Or long, whatever. Okay. Same thing here. your information can be byte or can be a word. And also I explain, if it is a byte, what is the minimum number and what is the range of numbers you can store there. For example, I mentioned here, if it is a byte and this number is unsigned, you can store number from 0 to until 255. Okay, so if you are measuring something and what you are measuring is unsigned and it is in this range, so byte should be enough. Okay, however, if you are measuring is more than this number, maybe it's going to be bigger than 255. In this case, you have to use a word, not a byte. You understand? You need bigger space. Okay. In case of signed, also you have a limit. This is the minimum. This is the maximum. Again, if the number you are going to measure or your variable is okay in this range, so byte is enough. If it is not, so you have to go for a word, and this is the range for word. Okay. So now the question is, you are telling us memory has locations. Every location is storing 1 byte. So now, what if my data is word? Word means 2 bytes. How can we do that? Okay, very simple. The way you are gonna do it, we are gonna store it in two locations, two consecutive locations. Okay. So for example, if this is a byte this way, I want to store this byte in the memory. I'm going to store it in 2 locations, 1000, for example, and 1001. Is that okay? So, and the way you are going to do it is the least significant byte are going to be stored at 1000. The most significant are going to go to it's going to go to next location automatically. You got what I'm saying? I'm going to say something. Please listen to me. I know it's confusing some students, but listen to me. That is why, look here. Later in this course, what we are gonna do is I'm gonna write instruction. I'm gonna say I want to store a byte in location 1000 or 2000, for example, any location. Or also are gonna write an instruction to say I'm gonna store a word in location 2000. Okay. How? So what happens here? This byte, okay, I'm gonna store it in this location 2000, which is okay. Because 2000 has a byte. It's only 1 location. It's a byte. It's okay. But I don't understand this one because this is a word. This word should be 2 bytes. And this is 1 location. Okay. It's very simple. So here, guys, just for short, I don't need to say 2000 and 2001, 1000 and 1001, 3000 and 3001. Just for short. Just when you give me one address, automatically, I'm going to get the next one automatically. You understand what I'm saying? So here, when I store a word, it's going to take this one and next one automatically. Okay. So one more thing here, if you look at the memory, guys, I know some students asked about this, were confused a little bit about this before. If you look at the memory, guys, for example, here, this is location 1000. I'm going to assume this 1000, this is, for example, speed. I'm measuring this motor. I'm measuring the speed of motor, speed, whatever, and then I'm going to store that here, okay? And then also in my program, I'm going to use a word for temperature, okay? And then I'm going to use 1 byte for example, for pressure. I'm measuring pressure or whatever, okay? Or count, you are counting something, okay? So this is 1000. So this one should be 1001, 1002, 1003. Okay. So what I want to tell you guys is that this is one information, right? So this is one information, the speed in 1 byte. The speed here in one byte. So every time I want to read the speed or I wanna write to the speed, so it has to be here. Similar to when you did, for example, I is equal to 2, speed is equal to 7. Okay, so every time I write to speed or read from speed, so I'm gonna read this byte here. Is that okay? However, if you look at the temperature is 2 bytes. 2 bytes. Okay, this 2 bytes is 1 number. You understand what I'm saying? So it doesn't make sense to just read this byte or this byte. It doesn't make sense. It doesn't have any meaning. That's what I'm saying. So these 2 numbers together, they create the temperature. That is why, if your program is correct, every time I want to read the temperature or I want to write to the temperature, I'm gonna read this. I have to read these 2 bytes together. You understand what I'm saying? this logic should be in your program. It's not in the hardware. If you tell the hardware, give me this byte, okay, the hardware is going to give you this byte. But what it means, it doesn't mean anything. You understand what I'm saying? Because these two should be together, because this is one number. Okay, so this logic should be in your program. You understand what I'm saying? Yes.
So when you put an N to it, you just need to do
No, when you write, you have to write to both. When you read, you have to read from both. Yeah, that's a good question. So my understanding from your question is, if I want to read this word, should I read it twice, one and one location? Okay, no, you should not do that. You have, as I'm going to teach you later, we have instructions to read or write bytes, and we have an instruction to read or write words. Okay, and you just use one instruction. However, how this instruction works, okay, this instruction is going to read them separately. Read this one and this one, but you don't need to write the instruction. You don't need to write each one. Okay, you just one instruction. But what I'm saying, we have instructions, as I'm going to teach you later, that can read the byte. So every time I want to read the speed, so you have to use an instruction that reads bytes. Okay. If I want to read the temperature or I want to write to the temperature, so you have to use in your program, you have to use the instruction that read or writes words. Okay. Now, one more thing, guys. If, for example, if you have a byte, I can say, for example, in this byte, we are storing 3A. Okay. For sure, I have to put dollars, and sometimes I'm lazy to add the dollar sign, but I mean hexadecimal, right? So this is a byte here. Okay. Let me tell you something. What if, for example, if it is 03 this way? Okay, it can be 03 this way. However, listen to me. However, for short, in my program, I can say I want to write 3, just 3 in a byte. Okay, so when you write 3, automatically it's gonna add 0. You understand what I'm saying? So if I wanna write, you can put the 0, you can say I wanna write 03. You can do that. Or for short, you can just say I wanna write 3. That's it. So automatically it's gonna store 03, just for short. You understand what I'm saying? Don't be confused. I know some students are confused here. Okay, don't be confused when I say, don't tell me 3 is only 4 bits. Yes, 3 can be stored in 4 bits. However, when I store it in a byte, automatically it's gonna put 03. Just for short, if you want to put 0, that's okay. Just for short, you can say I want to store 3 in a byte. You understand what I'm saying? Same thing here. When I say I want to store 3 in a word, I want to store 3 in a word. Okay. So what happens here? This is gonna be stored 0003. I don't need to put zeros in the left here. I'm gonna say I want to store 3 in a word. You understand what I'm saying? Listen to me. If I have 3, number 3, yes, I can store it in a byte. I can store it in a word. I can store it in a double word, right? So byte should be enough. And if it is bigger than a byte, also should be enough. You understand what I'm saying? However, if I want to, can I store, for example, can I say I want to store 3AF in a byte? Can I do that? No, you cannot do that because this one should be bigger than a byte, right? The byte has to be only 8 bits. This more than 8 bits. Okay. So I just want to same thing, guys. When I say I want to store this one in a word, what happened is it's gonna store 03AF. Just for short, sometimes I don't put this 0. Understand what I'm saying? Okay. Okay. So here I want to show you. This is how the computer works, guys. All the time, microprocessor is reading data from the memory or writing all the time, reading, writing all the time. Okay. And I want to show you here physically or how the hardware is going to read and write. So I want to give you an example here to understand it better. So as shown here in this example, I want to do something like that. The microprocessor wanna write number 70 in memory location 2000. Just any numbers. I'm just giving you an example. I wanna write number 70 in memory location 2000. Is that okay? Don't be confused. You are gonna write only one instruction to do that. Okay? I'm explaining how this instruction is gonna be executed. So you don't need to do these steps. Okay? Just write the instruction. I'm explaining how this instruction is gonna break it down. Because I cannot do this operation at once. I have to break it down, as you will see right now. So I have to do small tests, as you will see right now. Okay, so this will be only one instruction in your program. However, how it is executed? Okay, number one, the first task, microprocessor has to write number 70 to the data bus. So this is the first operation. On the data bus here, a microprocessor has to write 70 here. Number two, microprocessor has to write 2000 on the address bus. So now everything is ready for the memory to work, right? So I already put here 2000, I already put here 70. Okay, everything now is ready. The memory is not gonna work until I ask or until I command the memory to work. And this is the last one. The last one here, and the control bus is gonna send the instruction to the memory. It's gonna put here 1, and this one memory is gonna work. Okay, how the memory is gonna work? Very simple. This is hardware. I must tell you hardware. The location here, what happened? This memory in the location, because this is writing operation, writing in the location 2000. I'm gonna write whatever written on the data bus. In this case, it is 70, and the old value is gone because I overwrite it. And this is done. This is writing operation. One writing operation is done. Any questions? Makes sense, right? So number one, I have to put the data here. I have to put the address, and now everything is ready. So I'm gonna tell the memory start working. Once I do that, the hardware here is gonna store 70 in this location. The old value is gone. Any questions? Okay, let me give you another example for reading operation. Okay. For reading operation. So here for reading operation, I want to read the location 7000. Okay, how this can be done? Okay, let's think about it. The way it should be done, guys, is I want to read the location number 7000. Number one, we have to put here number 7000 here. Okay, that's number one. Number two, I'm gonna send to command to memory to read. I'm gonna tell memory read. In this case, the memory is gonna get whatever here as the address bus. Is gonna go to this location and get a byte from there, whatever is stored there, and put it here in the data bus so that my processor can take it. Okay, guys. So number one, it makes sense, right? So number one, I have to put the address on the address bus. Number two, read should be 1. Number 3, the memory should read whatever is there, 3F, 2F, whatever is stored there in this location, is gonna put it on the data bus, and then my processor is gonna take it from the data bus. Okay. Any questions? Okay, let's agree also in something here, guys. When I tell you location 7000, so I'm gonna write it this way. Okay, let's agree on this. But if I put brackets, square brackets like this one, as you see here, what is the difference when I tell you location 7000 and when I put square brackets like this one? Okay, when I put square brackets like this one, I mean the content, the byte stored in location 7000. That's what I'm saying. So in a quiz, if I tell you 7000 equal, yeah, you have to fill, you have to give me the answer here. So what this means? It means I'm asking you what is the value, what is the byte, okay, stored in the content of this memory location. Is that okay? Brackets here. This is not, this is just something we're gonna use in, but this is not a command. We're not gonna use it in the program, okay? But just in when I want to mean the content of the location, I'm gonna bracket this one. Yes. So yeah. Yeah, I'm gonna say the address 7000. I'm gonna just write the address 7000. Okay, let me see here. Now, so what I did so far, guys, I am here in this section. Here, guys, I told you any computer system should have memory. It should have input output device. It should have processor. Okay, and you can see from the arrows, look at the direction of the arrows. Here the data has to go this way. Here the data has to go this way. Here the data can go this way or that way, because I can read, processor can read or write. And all we don't have only one input or output device. We have number. We have a bunch of them. Okay, input output device. Okay? Now I almost explained everything here. So now I'm gonna move to the processor. So I want to give you some basic idea about the processor. Okay. For sure, any computer system should have a processor, right? So number one, what the processor should do, what the processor is doing. Okay, the very simple answer, very simple answer. This processor should do only one thing: execute instructions. That's it. Give me an instruction, I'm going to execute it. This is the only thing the processor is doing. You understand what I'm saying? And as I said, every instruction just a bunch of ones and zeros. Okay. And the hardware, as you will understand right now, the hardware is designed when you give me these ones and zeros. Okay. The hardware is designed to do certain operation, addition, multiplication, division, whatever, as you will understand right now. Is that okay? So let's agree on that. Microprocessor can do only one thing: execute instructions. Okay. Where are the instructions? The instructions are in memory. That's why it has to read them from the memory. Okay. So anyway, so here I'm gonna give you more information about, or I want to focus on the processor now. By the way, when I say processor or when I say CPU, or when I say microprocessor, all of them mean the same thing. Okay, there is no difference. CPU or processor or microprocessor, all of them are the same. Okay. Okay. So now I wanna teach more about processor. So as you see here, guys, the processor has three main component. I'm gonna discuss them now. So inside the processor itself, it should have what we call control unit. It should have arithmetic logic unit. Also, it has a register. So I want to explain every one of them here. Okay. So the processor itself, it has control unit. I want to explain what this one is doing. Arithmetic logic unit also has registers. Okay. All of them should work together to do one thing: execute instructions. Is that okay? Now, let's talk about them one by one. So let's start with the arithmetic logic unit. And I'm going to show something interesting here. So as you know, I think from maybe other classes, the arithmetic logic unit is used to perform the arithmetic and logic operation. Okay. So this is a hardware unit. Okay. This hardware unit should execute any arithmetic or logic operations. Is that okay? By the hardware or by the hardware. So here I want to give you a very simple. Here we have a very simple computer. Okay, so in order to explain the basic idea of how computers work, so here we have a very small computer. Okay, this small computer can execute only 4 instructions, as you see here. Add, it can subtract, it can end, it can do OR operation. Is that okay? So I'm going to explain how it works. So this is the arithmetic logic unit. Okay. This is a very small computer. This computer can only execute 4 instructions, very simple one. Okay. Just I want you to understand how instructions are executed. Okay, by the hardware. Okay. By the way, I said it many times. Okay. When I say machine code, the machine assembly, okay, is actually you are programming using machine code, and the machine code is executed by the hardware. So if you want to do addition, the hardware is going to do addition. Subtraction is done by the hardware. Okay. So here, the machine codes are executed by the hardware. Okay. And again, this is the reality. What you see in Java, in C, this is high level. This is not the reality. You understand what I'm saying? Because whatever you write in Java, this is not what the microprocessor is going to do. Okay, whatever you do in Java or C or any high-level programming language, it has to be converted to machine code, because the only thing processor can execute only the machine code. Okay, you will understand more. So now let's see how this one works. Okay, I'm going to tell you how it works. Look here, guys. We have here something we call opcode. Okay, so what I'm saying here, this is like a small computer. This small computer has only 4 machine codes. 4 machine codes, like 0, 0 for addition, 0, 1 for subtraction, 1, 0 for AND, 1, 1 for OR. Okay, what you are going to see right now, guys, and I want you to understand, for sure that's a very small computer, but I want you to capture or understand the idea. Okay, so what you are going to see right now, how when I put the code 0, 0 code, when I put 0, 0, this is machine code. When I put it on the hardware here, the hardware will do addition. I'm gonna give you some idea how this is done by the hardware. Okay, same thing here. How when I put 0, 1 here on the hardware is gonna do subtraction. Okay, how when I put here 1, 0 is gonna do addition. How when I put 1 is 1, 1 is gonna do another command. You understand what I'm saying? And this is what happens actually. What happens, as I told you, the machine code is stored in memory. I'm gonna ask the memory, give me the instruction. After I read the instruction 1, 0, 1, 0, 1, 0, when I put it on the hardware is gonna execute this instruction. If this instruction multiplication, the hardware is gonna do multiplication. Why? Because the hardware is designed this way. Okay. So as you will understand right now, guys, the hardware is designed when you put here 0, 0, okay, you will see it now. This one is on, this one is off, this one is on, this one. So same as the out, as a result, you are going to get addition. The hardware is designed this way, right? As you see right now. The hardware is going to be designed when I put 0, 1 here, I'm going to do subtraction. Okay. Same idea, how this is microprocessor should read machine code, put it in the hardware is going to do this operation. Anyway, so let's see how it works, guys. Here, but before I move forward, I just want to make a very quick revision about two units here. We have here other. This is hardware circuit other. I think you already should be familiar with. You already should have designed this one in the digital system course. Anyway, so this is a circuit. This circuit should do addition, hardware addition, bit by bit hardware addition. Okay. So also we have another one here. This unit. This is also logic circuit. It's called comparator here. This one it has 2 inputs. If the 2 inputs are equal, it should output 1 here. If the 2 inputs are different, it should output 0 here. Okay, I think let me here. Okay, so here this one is comparator. This one should also this logic circuit. Okay, logic circuit. It has 2 inputs as you see here. 2 inputs. If they are equal, I'm going to get 1. If they are not equal, you are getting 0. Okay. The last one here we have multiplexer. This multiplexer, as you see here, also this is a logic circuit, hardware logic circuit. Okay. This logic circuit should work this way, guys. We have one output, as you see here, and we have multiple inputs, as you see here, and we have what we call selector. Okay. What happens is that if you put here in the selector 0, 0, what it means when I put here 0, 0, that means this output has to connect it to input number 0. So here in the output, I'm going to see whatever here. So if there is 0 here, I'm going to get 0. If there is 1 here, I'm going to get 1. It's like a switch. So this one is like a switch this way. If you put 0, 0, so this one value is going to go out here. If you put number 1, number 2, number 3, that's multiplexer. Okay, guys. So as you see here, for example, if I put 1, 1, 1, 1 means number 3. So whatever here is going to be shown here, multiplexer. Is that okay? Using for sure, again, this is just a very simple computer. So using this very simple logic circuits, I'm going to show you how can we do like a small computer. Okay. So let's see. So now I promised you, I made a promise. When I put 0, 0, I'm going to get addition. When I put 0, 1, you are going to get subtraction. Let's see how it works. Look here, guys. When you put here 0, 0, okay, number 1, Is 0, 0 equal to 0, 1? No, it's not equal. Not equal, right? That's why I'm going to have 0 here, right? And because here I have 0, so this input is going to be connected here. Input number 0 is going to be connected here. Okay. And also because this one is 0, this multiplexer has, look here, we have two numbers. One is A, one is B. We have two numbers here, A and B. All the operations should be done on A and B. So if you want to add, I'm going to add A plus B. If I subtract, I'm going to subtract B from A. Or if you want to do and logic operation, it's going to be, this is the input you have, okay? So, and we have here inverters. I'm going to tell you why we need inverters here, okay? So here we have B, here we have B prime. B prime, you know B prime means one's complement, flip all the bits. Why? I'm going to tell you why, you'll understand it now. Interesting, look here. Let me continue. When I put here 0, 0, 0, 0 does not equal 0, 1. So the result here is 0. Because the result here is 0, so Cn is going to be connected to the other. Okay. Also, this one also 0. So I'm going to get B instead of B prime. So this one is going to be, and the A is here. So look at the input of the other. Should be A, B, and the carry. Okay, or C. Forget the C for now, because I'm going to teach you later why you need it. Okay. And then, so this other is going to do addition, and then it's going to be the result is here. Also, this is a multiplexer. When you put 0, 0, so the output here should be connected to here. This is multiplexer. When I put 0, 0, so the output should come from here, not here, not here, not here. It should come from here. Okay. So by this way, what I'm going to get here, I'm going to get the output of the other. The output of the other. Okay. So as you see here, the output of the other is A plus B plus Cn plus, forget the Cn for now, A plus B. Is that okay? You understand it better when I do subtraction, but for now, listen to the main idea. The main idea is that I designed the hardware so that when I put here 0, 0, this one on, off, I'm gonna get at the end addition. Okay. Let's see another example, you will understand it better. So now, when I put here 0, 1, 0, 1, okay? So when I put this code, I should do subtraction. So how this case is different from the previous case? I'm going to tell you, look here. So is 0, 1 equal to 0, 1? Yes, they are equal. So the result here at the output here is 1. Okay? And because this one is 1, so here, this input is going to come here. This input is 1. The input, as you see here, guys, is 1. Okay, and this input here, I'm going to get this input because this is also 1, which is B prime, and this one is A. Is that okay? So here the input of the other should be 1, B prime, and A. So what I'm going to get here, A plus B prime plus 1. A plus B prime plus 1. Is that okay? Which is A subtracted B. You get what I'm saying? And that's what I explained last time, by the way. I told you the good thing about the two's complement. The good thing about the two's complement. I don't need another circuit for subtraction, right? Because subtraction is just addition, right? That's why I used the one circuit, the same circuit. I used it for addition and subtraction. You get what I'm saying? Very interesting. So the way I did it here, in order to do subtraction, I'm gonna add A plus B prime coming this way, plus 1. A plus B prime plus 1 is take away 1, B, okay, and so on. So let's see, for example, and because here you put 0, 1, so because here you put 0, 1, so the output should come from here. Okay. Anyway, so let's see another example. Let's see another example. For example, here, if I wanna do AND operation. So you have here to put 1, 0. Okay. When you put 1, 0, so the output here should be connected here. Okay. And then this is A and this is B. So I'm gonna see here A and B. You got it? Okay, guys. Okay. Any questions? Okay. There are several important things I'm gonna explain right now, guys. Very important things. So let's agree on this. Okay. Every computer, again, we agree on the following, okay? Every microprocessor should have a set of instructions it can execute. And this instruction, we call them the machine code, okay, for each processor. Okay, so let me ask you a question. Why this one is 0, 0? Why it's not something else? Simply because the hardware is designed, when you put this number, I'm going to do addition. You got what I'm saying? So every processor, the company that manufacture this processor should give you a table. This table should have all the instructions this processor can execute, and it should have the machine code for each instruction. This one. You understand what I'm saying? So every company manufacture a processor, it should give you, okay, because the hardware is designed to execute a set of instructions. We call it instruction set. Okay, let me say here. Yeah. So here, what I'm explaining here something we call instruction set. What this means? It means the instruction set of a microprocessor is the fixed set of operations the computer can be programmed to perform on data. Okay, that's what we call instruction set. So when you buy a microcontroller or when you buy a microprocessor, the company should give you a list. This list should have all the machine code instructions. Is that okay? And for our microcontroller, you have a table like this one. I'm going to choose a table now. Okay. This table should have all the instructions this processor can execute. Also, it should have the machine code for every instruction. For example, if you want to do addition, you have to use this code 1806. And this code is called machine code. So this number 18, this is in hexadecimal 1806. Okay. So this number here, this is machine code. When you put this number on the hardware is gonna do this operation. Is that okay? So if you go to the course website, okay, guys, if you go to the course website here, you will find I give you here instruction set. Look here, guys. We're going to use this table. So you need this table, the instruction set. Let me open it. Okay. So this instruction set, let me, how can I open it? Okay. Look here, guys. So this table, that's what we call instruction set. Okay. Every processor should have a table like this one, right? It's not uniform. That means here we use 1806 for addition. Maybe a different processor is going to use a different number because it depends on how they make the hardware. Okay. Anyway, so for example, if I come here, guys, so this table has all the assembly instruction I'm going to teach. Okay, it has all of them. Okay. For example, let's see here. Just I want to show you here. So this one has all the instruction this microcontroller can execute. Okay, because this is hardware. I can modify this instruction. I cannot add one instruction or remove because it's hardware. All this instruction is executed by the hardware. Is that okay? There is a hardware circuit that can do all this operation. Multiplication, division should be done by the hardware. Is that okay? So anyway, so for example, if I come here, guys, let's look at so if you see here, guys, here, this is assembly code I'm going to explain. ABA. So when in chapter 2, I'm going to explain assembly in chapter 2. And chapter 2, I'm going to tell you if you want to do addition, this is the instruction you have to use. Okay, just like CN, C out in C language, but here in assembly, this on the English words, the instruction we are getting. ABA, is that okay? So this one should add a register A. I'm going to explain what I mean by register. So it's going to add whatever is stored in register A plus register B. So it's going to do addition. Okay. So what happens here, and the machine code for this one is 1806. Okay. This one ABX. So this one should be 1A E5. Okay. And what you are going to see, what you are going to see in the first lab is what you are going to see in the first lab. You are going to write assembly instruction like English words, assembly instruction like this one. ABA, ABX, ABY, and so on. Okay. And then you will see, we are going to use what we call a very simple program. We call it assembler. So this program should take your English, the English words here, it's going to convert it to machine code. Okay, this way. And so you will see when you use ABA, if you go to the memory location, you will find that it's stored 1806. You got what I'm saying? Okay. I wanted to, so now let's agree on several things now, guys. Number one, every processor should have a set of instruction it can execute, okay, by the hardware. Oh, and this all the instruction we have here. Number two, every instruction should have a code. Okay, this is the code here. Okay, this number two. Any questions? Number three, I want to explain something important here, guys. What is the difference between programming using assembly and programming using C language or Java language? Okay, maybe you know that, or you were told that C language is high level. You are very far from the hardware, right? Assembly is low level, and low level means it's very close to the hardware. That's the meaning of it. Okay. So now I want to clarify it more. I want you to understand better. Okay. Look here, guys. I don't see a big difference between programming using assembly or programming using machine code. It's almost the same thing. If you program using assembly or machine code, it's the same thing. Why you say the same thing? I'm going to tell you why. Look here, guys. Simply because of the following. Listen to me. We don't like numbers. We don't like numbers. We like English words. When you write your code, we like to use English words, okay? And this is the assembly. So what happens in assembly, you are going to use instruction English words like ABA, ABX, ABY, add A, and so on. So you're going to use English words this way. This is assembly, right? And then you are going to use a very simple program. Very simple program. We call it assembler. This program is gonna, it's like lookup table. It is like a lookup table. What this program is gonna do, every time you write EBA, I'm gonna replace it with 1806. That's it. Very simple program. So every instruction you write in this assembly, this is machine code. Okay. Again, I am saying if you program using assembly, it's gonna be the same thing like machine code. Okay. Well, the only difference is it instead of writing 1806, okay, I'm gonna just use English names, okay? Because it's more convenient for us. Imagine if you do a program and write 18, 17, 20, it's gonna be too difficult to write programs this way, right? It's easier to just use English names. Add, subtract, multiply, okay? So every instruction you write here in assembly is gonna convert it to one instruction in machine code, one by one. It's like you replace lookup table, replace. When I see this one, I'm going to replace it with this one. Very simple. That's why I'm saying assembler is a very simple program. Is that okay, guys? And that's what we are going to see in the first lab again. In the first lab, you are going to write the instructions assembly, and you will see by yourself how it is stored in memory, right? So this one is going to be stored in two locations, 1806 in two locations. Because we agreed every location should store 1 byte, right? Yes.
I was just wondering if there's anything more.
Very small things I'm going to explain later, but very assembler, because there is something else called compiler. So let me explain it now. Just yeah. Look here, guys. I want to explain what is the difference between assembler and the compiler. What is the difference between them? Okay. Okay. Assembler, if you write program in assembly, and as we agreed, assembly, you are going to use English words, subtract, multiply, because this is more convenient for us. Okay. So I'm going to use assembler to convert these English words to machine code. Okay, and I told you this assembler is a very simple program. It doesn't do much work. It just this English word, I'm going to replace it with this number. You can even do it by yourself. Very simple program. Is that okay, guys? This is assembler. Okay. However, if we come to compiler, compiler is a completely different story. Compiler is a completely different story. Why? I'm going to tell you why. Compiler is used in case of high-level programming language like C. Okay, this number one. What compiler should do? It has to take the compiler. It has to take your C program and convert it to machine code. Okay, so when you write your program in C language, the compiler is going to convert it to machine code. So they are the same. This one is going to take assembly program, convert to machine code. This one is going to take C program, convert to machine code. They're the same. No, they're not the same. Very big difference between them. What is the big difference? I'm going to tell you what is the big difference. Look here. C language is high level. High level. Okay. We hide a lot of the details. The details are hidden. Okay. That means, okay, that means maybe one instruction you are going to write in C language, when it is converted to machine code, I have first to this instruction, it should be equivalent to 10 or 20 instruction in assembly or in machine code. You got what I'm saying? Okay. But here in assembly, every instruction you write in assembly is going to convert it to one instruction in machine code, one to one. But this one is high level. Okay. So maybe one instruction you are going to write in C language, first it's going to be converted to 10, 20, 30, 40 instructions, and then in machine code. Okay. That's why compilers are much more complicated. That's why the people doing a lot of research. How can you make compiler smarter, more efficient? And many people are complaining, listen to me, but this important point. Many people complaining that compilers are not smart enough. What you mean it's not smart enough? Because they are doing a very difficult job, okay? I'm going to tell you what I mean. And this is something in favor of assembly, okay? So let me explain it. Okay, some people are saying, if I want to do something, so if I program it in assembly, so I need this amount of instruction, if I program it in assembly. However, if I program it in C, I'm gonna need this amount of memory. So simply because the compiler is not efficient. The compiler is not efficient. Okay, so you just write it in high level. When it is converted to machine code, it's gonna be too many instructions. Okay, that is why still too many people love assembly. That's why many people are saying, if you want to do a very fast program, if you care about efficiency and you want to do something very fast, you should program it using assembly, not C language. You got what I'm saying? So let me see it again, guys, for the last time. Let's agree on this. This is a very important point. Listen to me. First, let's agree on this. Microprocessor can only understand machine codes. Okay, it's the only language, the only thing microprocessor can execute, right? Number two, if you write assembly, English words, it's going to be converted to machine code. Okay, and this conversion is very trivial, very trivial. You can do it by yourself. Just one instruction, I'm going to replace it with just a bunch of ones and zero. But I can say assembler is just more convenient to me. And instead of programming 1, 2, 3, 4, 5, 6, 8, 9, 20, it'll be too difficult to program this way. So assembler is very trivial program. It's going to take one instruction here in assembly. It's going to replace it with only one machine code. Okay, one by one. Very trivial program. However, C compiler is much more complicated. Why? Because it's high level, right? High level means one instruction in C has to be, when it is converted to machine code, that's why the compiler has to be smart, okay? It has to convert it to 10, 20 instructions, okay? So for example, in C language, you used to have for loop, while loops. Hardware, this is your language. The hardware doesn't understand for loop or while loops. This is yours, right? So compiler has to convert it to what can be done by the hardware. Okay, guys, any questions? Is that clear now? What's the difference between compiler and assembler? Okay. And now you understand what I mean by machine code. Just a bunch ones of zeros. When you put it in the hardware is going to do this operation. You should understand assembly language. Everything you write in assembly is going to be executed by the hardware. But when you do for loop, like what you did in C language, this is not going to be done by the hardware. There is nothing in the hardware. It has to be converted to something. It's going to do for loop. Yes, you are going to do for loop on the hardware. That's true. But it's not. There is for itself. There is no command in the hardware for 4. You understand what I'm saying? Anyway, so let me go again. So this is, guys, this all the instructions I'm going to teach here. This is the English name we're going to use for the instruction. Okay. Okay. So this is the English name we're going to use for the instruction. Here, description to the operation, what this instruction is doing. Don't worry about this because that's what I'm going to do in chapter. We have many instructions, as you see here. We have many instructions. I'm going to teach most of them in chapter 2. Okay. Also, you can see here, at least I finished one column here. So you can see here, sorry. Yeah. As you see here, guys, this is the machine code for each instruction. You can see here, guys, they are not the same. Some instructions, look here, some instruction is going to take 2 bytes. Look here, this is 2 bytes, 1806. They are going to store in 2 locations, 1806. You understand what I'm saying? Okay, and here 1A, E5, 2 locations. So you can see here, they're not the same. Some instruction is gonna take 2 bytes, right? This is the space, right? This one is gonna take, some of them is gonna take 3 bytes, 4 bytes. We have 4 and so on. So they're not the same. You understand what I'm saying? So some instruction is gonna take 2 locations in 2 bytes, 3 bytes, 4 bytes. It depends on the size of the instruction. Any questions? Yes.
So is that, for instance, 1806, technically 00, 1806?
No, this has nothing to do with the location. Okay, this is the content. Is that the content stored in memory? Okay, what about the location? As I'm going to explain in this course, the location you are going to when you write your program, you are going to tell. Okay, I told you this is a good question. So let me explain here. So what I'm saying, I told you in memory should store 2 things, data and to program. Okay. When I teach assembly, I'm going to tell you, you have to tell. Look here, guys. Here, the good thing about assembly, you can see all the hardware. You can see all the details. You have full control. You have full control on everything. For example, in C language, you say integer I. Actually, I is stored in memory, and you may not know where exactly in memory. You don't have much control in that. Here you have full control. For example, as I'm going to teach in assembly program, guys, we are going to use here on instruction, we call it org. Okay, I'm going to say org, for example, 1000. And then we are going to put all the data here. And then I'm going to say org 4000. This is assembly. And then here you put all the instructions here. What this means? I'm going to tell you what this means. It means I'm asking the assembler, okay, this is my data, put them starting from the location 1000. So I want to store the data starting from 1000. It's going to go all the way. Okay. Here, org 4000, that means this instruction should start from 4000. So it's up to you. Here you have full control, right? So you can manage it as you want. You can put them anywhere in the memory. You understand what I'm saying? So this is about the location. Okay, what I'm explaining right now is when I say, for example, when I write in an instruction EBA, when I read this instruction here, what's going to happen? I ask it here to start from 4000. I ask it to start from 4000. So what's going to happen is starting from 4000 is going to put 1806. Okay, because this one should be 1806. And that's what you are going to see in the coming lab. The coming lab, you are going to write the program, and then I'm going to ask you to go and go to this memory location, see your machine code after it's converted to machine code. Okay. questions? And again, this hexadecimal. When I say 18, it's gonna actually be 0018100, but I'm just putting it in hexadecimal. Okay, any questions? Okay. Okay. So now you should understand, guys, what I mean by machine code. You should understand what assembly, how assembly is different, how assembly is similar or different from machine code, how assembly is different or similar to C language, what is the difference between assembler and to compiler. Okay. You should also understand what is the meaning of machine code. Again, machine code is just a number, ones and zeros. When you put it in the hardware is gonna do this operation by the hardware. You should understand every instruction, every assembly instruction is gonna be executed by the hardware, supported by the hardware. It's gonna be executed by the hardware. Okay? And also you should understand all the instructions are stored in memory. So 1806 is stored in memory, right? All what I'm gonna do as a processor, I'm gonna take the memory. I wanna read this instruction. So I'm gonna read 18. I'm gonna read 06. Now I have the instruction. Put it in hardware, execute it. I'm done. Then I'm gonna go to the memory. Get me next instruction. 0729, whatever. I'm gonna put it in the hardware, execute it, go to the memory, read next one, and so on. Is that okay, guys? Okay, so let's see. Now, as I told you now, the processor should have control unit. I'm going to explain what is control unit. I already explained arithmetic logic unit. Now I'm going to also explain registers. What do you mean by register? So register is one of the components of processor. Every processor should have register. Please tell me, what do you mean by registers? How they are used? But also keep in mind, everything here in the processor should help to do one thing: execute an instruction. Everything here should support this, because it's the only thing the processor is doing. Just execute an instruction. Is that okay? So let's see what you mean by registers. Okay, I'm gonna tell you what I mean. Okay. So okay, guys, let's see. What do you mean by registers? Registers are storage units. Registers are storage units. Okay, so every register should store some data, bytes, words, and so on. Okay, so storage units. Okay, okay, so, but you told us we have memory. So how they are similar to memory and how they different from memory? Memory also storage unit, right? Memory is used to store data. The same thing here. Registers are used to store data. So how they are similar? What is the similarity and the differences here? Okay, I'm going to explain. Look here, guys. Number one, registers are inside the microprocessor. Memory are outside the microprocessor. This is one difference. Okay. Second difference. Registers are very few registers. You don't have too many. Maybe you have 5, 6, 7, 8. It depends on the registers. Okay. So we have very few registers. Memory, we have too many locations in the memory. Both of them store data, but what kind of data? Because this is the main issue here. Okay. So number one, registers are inside the microprocessor. They are very few. Memory, we have many locations in the memory, right? Memory is used, as I explained, to store data, your data, and also your program. Okay. Registers, storage units inside the microprocessor, they should help the microprocessor to execute instructions. They are not going to be used to store program. They are not for that, because the program is here. They just, to execute an instruction, I need storage. Sometimes I'm going to give you an example to understand better now. Okay. Again, the whole processor is doing only one thing: execute an instruction. When I execute an instruction, When I read information from memory, I want to put it in some location, then I'm going to multiply, I'm going to do operation. So I should have some temporary storage to the data to do operation in this. So it should help the processor to do operation. Let me give you example before I take your question. But let me give you example. Here, I want to do something like that, guys. Okay. So look what I'm writing here. Registers should help microprocessor to execute instructions. They are storage, they store data. Yes, that's okay. So for example, I'm giving you example here to understand better what this means. Okay. I want to add the content of memory location 1000. I want to do this operation. I want to add the content of memory location 1000, which is 3A. I want to add this byte to the byte at the location 2000, and I want to store the result at 3000. Okay, so I want to add this byte plus this byte, store the result in this byte. This is the instruction, one instruction. Is that okay? Okay. How microprocessor is going to execute this instruction? How? I'm going to tell you how. So number one, look here, guys. Number one, the microprocessor has to do reading operation. Listen to me, because this is I'm gonna need this one just shortly. Okay. One instruction, I'm gonna break it down. I'm gonna break it down to tests. Okay. I'm gonna do one by one. Okay, as you see right now. I want to do this operation. This is just one instruction. Okay. So I am gonna do it in steps. Step number one. Okay. I'm gonna read the data at the location 1000. I have to store it somewhere. It's number one. Okay. Number two, step number two. Again, you are not going to do that. You just write the instruction. I'm explaining how this instruction hardware is going to execute it. It's going to execute it in steps, but you don't need to write these steps. Okay, you don't need to code these steps. You just write the instruction, but this instruction is going to be executed in small steps. Okay. Step number one. Microprocessor has to do reading operation to read this byte at this location is stored somewhere. Number two, the processor has to read the data or the byte at the location 2000, and then it has to store it somewhere. Number three, now I have this one and this one. I need to add them together and I have to store the result somewhere. Then I'm gonna do writing operation to store this one here, in this location, 3000. When I say somewhere, what you mean by registers, right? So registers are not gonna be used to store programs. Okay, registers are used just to help a microprocessor to execute instructions. Is that okay? I give you a very good example here. Any question, guys? Yes, there are several differences. Number one, registers are inside the microprocessor. Memory is outside the microprocessor. There's one difference. Second difference, registers are very few, maybe have 5, 6 bytes, no more than that. For memory, we have too many, like 65,000 bytes. We have too many, right? The most important part is memory is used to store data or store program. However, the registers are used to help the microprocessor to execute instructions. That's it. So the microprocessor doesn't have storage space to store the program. Okay. Good. Now, I'm gonna give you some rest, but not now. 10 minutes more. So I'm not gonna keep teaching until 7:15. Okay, so don't worry about it. So now. Okay. Now, guys, I want to explain something also very important, very, very interesting. Okay, listen to me. We have something we call it clock. Okay, okay, listen to me. So we have something here we call it clock. So what is clock? How it is useful? How it is used? What it means? Okay, I'm gonna tell you what it means. Look here, guys. Any computer system needs clock, something we call it clock, to work. Okay, So this is something needed in any computer system. The answer is yes. Okay. So what is clock? Clock here means square wave. The square wave this way. We call it clock. This square wave should be input to the microprocessor. That's what we call clock. The clock is just a square wave. It's input to the microprocessor. And every computer system should have a clock. So your laptop has a clock. Your smartphone has a clock. So our chip has a clock, and so on. Okay? So and the clock just a square wave. Okay. So how it is useful? How you are telling this something very important? Yes, I'm going to tell you how. Look here, guys, how it is useful. Look at the idea. I mentioned right now, or in several places, I mentioned to execute an instruction, I have to do it in steps. Step number 1, step number 2, step number 3. Right? So this instruction, I'm gonna break it down into tasks, small tasks. You know what I'm saying? I have explained right now. So for example, if I want to do, if I want to do this operation, so I have to do this step 1, 2, 3. Okay, so I have to, and it has to be in order. So I have to do this one first, second, third. So I have to do in a certain order. Also, I explained before. Let me go back. Yeah, I explained here. If you want to read a location from the memory, where I did it. Yeah, if you want to read a location from the memory, you have also to do some steps. It's not here. Yeah, look here, guys. If I wanna write to the memory, so number 1, I have to do this step. Number 2, I have to do this step. Number 3, I have to do this step. So this should be steps. Okay. So clock should help the microcontroller to do these steps. How? I'm gonna tell you how. Look here. Before I continue, let's agree on something. Every instruction, we're gonna break it down into subtasks, small tasks, right? So small tasks. I'm gonna execute the instruction. Okay, most of the instruction I cannot do it only at once. Okay, so I have to do it in subtasks. Okay, like this one. Okay, number 1, do this one. Number 2, do this one. Number 3, together. I did one instruction. Okay. So how clock should help here? I'm gonna tell you how. A clock, as I told you, just a square wave. Okay. In this square wave, guys, in every cycle, I can do one small test in every cycle. So this cycle, in every cycle, I can do one small test, right? So if one instruction needs three tasks or 3 small tasks, so I need 3 cycles. I'm gonna do step 1 here, step 2, step 3. You understand what I'm saying? So clock should help the microprocessor to execute an instruction. How? Every instruction should have like steps, right? So in every cycle here, the hardware is going to execute one step in every cycle, right? So and as you will see right now, some instructions is going to need only two cycles. Some instructions are going to do 2 steps or 2 cycles. Some instructions are more complicated. They need 6 or 7 cycles. Make sense? Because it depends on how much work this instruction is going to do, right? If the instruction is complicated, that means I need more cycles, more steps. Is that okay? By the way, clock is not something new. You should be very familiar with it. How you are very familiar? You should be very familiar with it. When you buy a laptop, they tell you this laptop is 2.2, 2.4, 2.5, right? What this number is? This is the frequency of the clock. Frequency of the clock. You get what I'm saying? And the higher the frequency, the faster the computer. Makes sense, right? Faster. Why? Because think about it. Why? Because, for example, if one instruction needs 3 cycles, right? The higher the frequency, the 3 cycles are going to be very short time. The higher the frequency, so I can do the instruction test. You understand what I'm saying, guys? So that's what we call it clock. Any computer system should have a clock. Okay. Any instruction you should know how many cycles needed in every instruction. Okay, guys? Let's focus on our microcontroller. How much is the clock in our microcontroller? In our microcontroller, the clock speed, sorry, I made a mistake here. It's 24. Okay, it's 24 megahertz, not 25. 24 megahertz. Okay, that means the time, this is the frequency, it should equal 24 megahertz. Okay, that means the time from here to here, okay, should be 1 over f. So it should be 1 over 24 megahertz or 1 over 24 microsecond. This is the time for 1 over 24 microsecond. This one here. So every task, every small task, I can do it in 1 over 24 microsecond. Okay. Some instruction is gonna need 2. Some instruction needs 3, 4, and so on. Is that clear, guys? Or still not? If you have any questions, just raise your hand. I'm not gonna penalize you if you ask a question. So if anything is not clear, you raise your hand. What I'm saying, every instruction, okay, I have to do it in steps or subtasks, okay? And some instruction is gonna need 2 tasks. Some instruction needs 3 or 4. I'm gonna tell you how can you know, right? So, and for every task should be 1 over f, 1 over the frequency should be 1 over 24 microsecond. Okay, guys? So now the question is, how can you know? Because this will be a question, I think in the quiz, I don't remember, not maybe, it's going to be a question anyway in the assignment I'm going to post. So you will need it, and everywhere I'm going to ask this question. So here, for every instruction, so for example, look here, guys, this instruction here, you already know what is the machine code, okay? So you already know for every instruction, how can you get the machine code? And I need you in the coming lab, okay? I need you to check after you convert the assembly to machine code. I need to go to the table and to check if ABA converted to this value or not. Anyway, so now my question is, I told you every instruction needs cycles, certain number of cycles, okay? How can you know from the table here? How can you know from the table? I'm going to tell you. Look here, guys, in this one here. Okay, so here we have 2 letters. 2 letters. Every letter means every letter refers to one operation done in one cycle, and they are defined here. So if I go up here, you see all these letters are defined here. So I'm not gonna. So here it's explaining what P means, what R means, what O means, and so on. What N means, and so on. So anyway, I'm not gonna go that far, but what I want you to know, guys, here is that here this instruction is gonna take 2 operations, operation O and operation O, 2 operations, and every operation needs 1 cycle. So this instruction is gonna take 2 cycles. What about this one? This one is gonna take operation B and then operation F. So this one is gonna take 2 cycles. Okay, and so on. You can see some instruction here. It needs many cycles, but this one, 1, 2, 3, 4, 5, 6 cycles, right? This is because it's a complicated instruction, right? It has to do a lot of work. Anyway, so they are not the same. So simply you can count here, guys. You can count how many cycles are needed by every instruction. Is that okay? Let me ask you a question. If I ask you, what is the execution time? How much time it takes to execute this instruction? Can you calculate it? Because this will be a question in the assignment. How much time is going to take to execute this instruction? Can you calculate it? Yes, how can you calculate it? Yes. Yes, for example, this one, you're right. This one needs 2 cycles. Okay, then. Yes, it's 24 megahertz. So the cycle is 1 over 24 microsecond, right? So all what you have to do, that's right. All what you have to do is, I'm gonna multiply 2 times 1 over 24 microsecond. This is how much this instruction is gonna take. You got what I'm saying?
Will our frequency always be 24 megahertz?
Look here, for our microcontroller, the maximum is 25, and it's programmable. So, but this is like advanced topic, okay? And we are gonna fix it to 24. So always we're gonna use it 24, but you can program it, you can make it less, but there is no, we're not going to teach this one, okay? Or we don't need, so I'm going to be fixed 24, okay? So I want you to imagine what 24 means. What 24, okay, look here, guys. That means in 1 microsecond, it can execute 24 cycles, 24 cycles in 1 microsecond, right? So, and this instruction is going to need 2, right? That means I can execute this instruction 12 times. So if I read this instruction 12 times, so this code is going to be executed only in 1 microsecond. You understand what I'm saying? So if I read this instruction 12 times, and everyone is going to need 2 cycles. So all of them are going to need 24, right? And everyone is going to 1 over 24 microseconds. So all of them are going to need only 1 microsecond, right? I want you to imagine how fast the computers are. And this is very trivial, very slow. 24 megahertz is nothing. You understand what I'm saying? Computer comparing to your smartphone, comparing to your laptop is nothing. You understand what I'm saying? But still you can do a lot of things using this microcontroller, okay? Which is not bad thing, by the way. I said it before. I want to repeat it here. It's not bad thing to have our microcontroller is not fast. We don't have big memory. It's not a bad thing because I don't need. I'm going to use it for a specific task to control arm of a robot. To control the arm of a robot, you don't need a very fast processor. You don't need large memory. So it should be enough. Okay. Simply because if you want to add more speed, if you want to add more memory, it's going to cost more money. And I don't need. If you need, that's okay. You understand what I'm saying? Before I think I can give you, okay, I can give you a list, but before I give you a list, so now I just wanna summarize the last part here so that I can start from a new stuff here. Yeah. So here, guys, I think this also will be a question in the assignment. If I have a program, a code or a program, if I ask you how much time it's going to take to execute this program, how much time? Okay, very simple. You need to count. This instruction is going to take 2 cycles, 3 cycles, 4 cycles, 2 cycles, 3 cycles. You need to add how many cycles total. For example, if I find it is 150. Total 150 cycles. So I'm going to multiply 150 times 1 over 24 microseconds. And this should be how much time I need to execute this program. Okay. Also, we are going to do in chapter 3, we are going to do something interesting in chapter 3. Okay. In chapter 3, we have one LED. I'm going to, you know, we have here. Look here, guys. We have LED here. Can you see the LED here? Yeah, this LED here. Okay. In chapter 3, we are going to do flashing LED. Flashing. Flashing means you turn on for 1 second, off for 1 second, on for 1 second, off for 1 second. Is that okay? You know how we are going to make this 1 second or half a second? How can we make it? There are different ways, but in chapter 3, I'm going to execute one way. We are going to do this way. Look here how we are going to do it. Number 1, I'm going to write an instruction to turn the LED on. Then I'm going to wait 1 second, turn it off, wait 1 second, and then repeat. This is how the program is going to look like in chapter 3. Turn on, wait 1 second, turn off, wait 1 second, repeat. Okay, this is how can you make flashing. Okay, now how can you wait 1 second? How I can make this one? We're going to do something interesting. Okay, what we're going to do to wait 1 second is I'm gonna execute instructions. Okay, I'm gonna execute a number of instructions. Okay, this one instruction logically they don't do anything. Okay, there is no logic. I just want to waste time. You get what I'm saying? So that once, in order to wait 1 second, once I come here, this one is gonna take few microseconds. After I finish all of them, I should have spent 1 second. You got what I'm saying? Anyway, this is not the best way, but this is one way to do it, to introduce a delay. To introduce a delay, I can just put a bunch of instructions. This instruction is going to take a certain time to execute this instruction, okay? But actually, this physical or logically, this instruction is not doing anything useful. You understand? Add, subtract, add, subtract, add, subtract. So at the end, you are not doing anything. I just want to waste time. Anyway, so it's something related to what I'm explaining now, but for sure, I'm going to explain it later. So, okay. Okay, so now I'm not gonna teach, we need to take some rest, but before to do that, I just wanna tell you, I explained here, guys, for assembly, we have English words here for assembly. These are the instructions I'm gonna teach in chapter 2. Also for every instruction, you can see here in the table, you can see what is the corresponding machine code for this instruction. In the coming lab, I want you to see, you are gonna write English words, and then these English instructions are gonna be converted to machine code, and they should be stored in memory. So I want you are gonna see in the coming lab, okay? You are gonna see in the coming lab how they are converted and stored in memory, right? Also, for any instruction here, you can tell how many cycles it needs, how much time it's gonna take, okay? Anyway, I think that's enough for now. We're not gonna, we need to take some rest. So let's take 10 minutes rest, and then we're gonna continue. Okay, so until 6:05. For the Zoom students, I'm gonna turn off the Zoom, and then I'm gonna turn it on after 10 minutes because I wanna download this video. Okay.
Okay.
So don't. So I'm gonna connect after 10 minutes. Okay, Zoom students.
All right. Thank you.